In question 1, we are asked to integrate this expression with respect to x, giving our answer in the simplest form. We start by writing this as x squared over 2x cubed minus 5 over 2x cubed dx. I will write the integral in index form, so it's 1 over 2 times 1 over x minus 5 over 2x to the minus 3 dx. The integral of 1 over x is ln of absolute value of x minus 5 over 2. I increase the power by 1, I divide by the new power, and I have the plus c as it is an indefinite integral. This simplifies to a half ln x plus 5 over 4 x to the minus 2 plus c. In question 2, we are asked to sketch the curve with equation y is 3f of 2x. We need to show all the cuts on the y-axis, any maximum or minimum turning points. So we've got two transformations here. The 2x means that we divide x by 2. So it's a stretch along the horizontal scale factor of a half, and the 3 outside is a stretch along the vertical scale factor of 3. So we multiply the y by 3. So all x values to be divided by 2 and all y values to be multiplied by 3. The resulting graph looks something like this. So we've got the maximum at a half, 6. We are cutting through the origin as the original graph, and the original cut on the x-axis, which was at 3, 0, is now at 3 over 2, 0. In II, we've got y is f of minus x minus 1. So the minus x is corresponding to a reflection along the y-axis. So we are multiplying all the x's by -1. So we are reflecting along the y-axis. And the -1 outside means that we are deducting 1 from y. So it's a translation 1 unit downwards. So the resulting transform graph should look something like this. So we've got now a cut on the y-axis at -1. The maximum is at -1, 1, and the minimum is at -3, -1. In question 3, we're given f of x here and we need to express it in this form. I will start by factorizing the denominator over here. So we've got that f of x is 3 minus x minus 2 over x plus 1 plus 5x plus 26 over 2x minus 5x plus 1. So the LCM here is 2x minus 5x plus 1. So we will express everything with a common denominator, hoping for some simplifications. So this will be 3 times 2x minus 5 times x plus 1 minus x minus 2 times 2x minus 5 plus 5x plus 26 and all over 2x minus 5x plus 1. We will proceed in expanding. It's 3 brackets 2x squared plus 2x minus 5x minus 5 minus brackets 2x squared minus 5x minus 4x plus 10 plus 5x plus 26 all over the denominator of 2x minus 5x plus 1. And we will now expand further to get 6x squared plus 6x minus 15x minus 15 minus 2x squared plus 5x plus 4x minus 10 plus 5x plus 26 and all of it over 2x minus 5x plus 1. Now we collect like terms in the numerator. We see that we get 4x squared plus 5x plus 1 over 2x minus 5x plus 1. And we notice that the numerator factorizes further into 4x plus 1, x plus 1. So the denominator is still 2x minus 5x plus 1. So the x plus 1 factor cancels out, and we are left with 4x plus 1 over 2x minus 5, which matches the form that the question was asking for the final answer. B, it says, hence find the f inverse of x, and then we need to find the domain of f inverse. Now, to find the inverse of any function, the first thing to do is write the function as y is equal to, so in our case it's y is 4x plus 1 over 2x minus 5. We interchange x and y, so x is 4y plus 1 over 2y minus 5. We're trying to make y the subject, so if I cross multiply, I get 2xy minus 5x is 4y plus 1, which takes me to 2xy minus 4y is 5x plus 1. I will factor out the y, so y brackets 2x minus 4 is 5x plus 1, which means that y is 5x plus 1 over 2x minus 4. So f inverse of x is 5x plus 1 over 2x minus 4. Now we'll proceed into finding the domain of f inverse. Now I will start by noting that the domain of f inverse is the range of f of x. So I will actually plot f, and based on my graph, I will decide on the domain of f inverse. So we had that f of x was 4x plus 1 over 2x minus 5. And we have the restriction that x is greater than 4. For the moment, I will ignore the restriction. I will start by noting that we've got a vertical asymptote when the denominator is 0. So the function is undefined if I've got division by 0. So we've got an asymptote at 2x minus 5 is 0. So that means that when x is 5 over 2, we've got an asymptote. Now to find the horizontal asymptote, I consider the behavior of f of x as x tends to infinity. So as x tends to infinity, the plus 1 and the negative 5 become insignificant. So f of x tends to 2, which is the ratio of the coefficients of x, 4 over 2. I can also say that f of 0 is simply minus 1 over 5. This will be the cut on the y-axis. And also when y is 0, we get that 0 is 4x plus 1 over 2x minus 5, which means that x will be minus a quarter. So this will be the cut on the x-axis. I think we've got enough information for us to draw a sketch. So there's a pair of axes here. We've got a vertical asymptote at the x is 5 over 2. There it is. So this is x is 5 over 2. We've got a horizontal asymptote at y is 2. So I'll draw that as well there. And we've got a cut on the negative x and the negative y. So it's a reciprocal graph. It must be something like this. So we have a cut here at minus 1 over 5 and another cut here at minus a quarter. And now it's the time to impose the restriction that x is greater than 4. Now, when x is 4, I will substitute, and I see that f of 4 is 4 times 4 plus 1 over 2 times 4 minus 5, which is equal to 17 over 3. So I've got an empty circle here as it's a strict inequality, and then this here is the 17 over 3. So the restriction that x is greater than 4 means that my function is only this part here, and therefore the range is between 2 and 17/3, both inequalities being strict. So f of x is between 17/3 and 2, and therefore I conclude that the domain of f inverse will be between 2 and 17/3. In question 4, we are given f of x is the modulus of 3x plus a, and we need to find the coordinates of the vertex P here. We know that the vertex is where the modulus expression vanishes, becomes 0. So we know that at P, 3x plus a is 0. So 3x is negative a, which means that x is minus a/3. We can also see that if 3x plus a is 0, so this goes away, then f of x is just a, so y is a, and therefore we've got the point P having coordinates minus a/3, a. And then in part B, we need to sketch g of x is the modulus of x plus 5a. I will actually do some preparatory work before I actually consider g of x. I will go to f of x and I will identify each of the line segments with its equation which does not involve the modulus sign. So on the right, it's y is 3x plus a plus a. So the modulus behaves like a normal set of brackets, which simplifies to 3x plus 2a. And on the left-hand side, we've got y is minus brackets 3x plus a plus a. So y is minus 3x. So the minus a with the plus a will cancel out. We can see that the cut on the y-axis is at 2a. And now I can proceed into considering what the graph of g of x will look like. I will start again by splitting this. So we've got that g of x is the modulus of x plus 5a. So we know that it's going to be simply x plus 5a if x plus 5a is greater than or equal to 0. And it's going to be minus brackets x plus 5a if x plus 5a is less than 0. This gives us x plus 5a for x greater than or equal to minus 5a, and minus x minus 5a for x less than minus 5a. So this is obvious now that something magical is happening at minus 5a. It's the overtake between one and the other. That's where the vertex is to be found. So the vertex has x coordinate minus 5a, and it's obvious that when x is minus 5a, then the y value is simply 0. So we are now ready to sketch g of x. We know that the vertex is at 5a. We've got a line that's cutting through at 5a, and it's less steep than the line already drawn here. So this here is 5a, and this is y is x plus 5a. And on the left, it's the line y is minus x minus 5a. So we've got the cuts on the x-axis, on the y-axis, everything is there. And then it says, find in terms of a the coordinates of the 2 points where the two graphs meet. So we're looking at this one and this one. The fact that I have identified each line segment with its equation means that I can easily see that to find this point here, I will equate this with this, and to find the other point here, I will equate this with this. So this makes our life a lot easier for part C. So for C, we've got x plus 5a is equal to minus 3x. So 4x is minus 5a, so x is minus 5a over 4. When x is minus 5a over 4, y is minus 3 times minus 5a over 4, which gives an answer of 15a over 4. So this is the first point, the point with coordinates minus 5a over 4, comma 15a over 4. And the other point is found by equating x plus 5a with 3x plus 2a. So we've got 3a is 2x, so 3a over 2 is equal to x. So y is 3a over 2 plus 5a. I'm substituting into one of the straight lines. So this is 13a over 2. And therefore the coordinates of this second point of intersection are 3a over 2, comma 13a over 2. In question 4, we've got this equation here for the temperature inside an oven T minutes after the oven is switched on. Given that the initial temperature was 18 degrees, find the value of A. So in other words, when T is 0, we know that theta is 18. So I will substitute this into the given equation. So I get that 18 is A minus 180 e to the 0. So 18 is A minus 180, which means that A is 198. Now the temperature inside the oven 5 minutes after is 90 degrees, and we need to find K in the form P, ln Q, where P and Q are rational numbers to be found. So we have that when T is 5, theta is 90. So 90 is equal to the value of A, 198, minus 180 e to the minus 5k. So we can say that 180 e to the minus 5k is equal to 108, which means that e to the minus 5k is 108 over 180, and this simplifies to 3 over 5. I will take ln and say minus 5k is ln of 3 over 5, and therefore k is minus a fifth ln of 3 over 5. I could stop here, or I could take a further step and say this means that I could take the negative 1 as a power to the 3 over 5. So this can be written as a fifth ln of 5 over 3. Hence, find the temperature 9 minutes after the oven is switched on. So we simply substitute. We say that when T is 9, theta is 198 minus 180 e to the minus 9k, where k is the value we just found here. Put everything on the calculator. I get 126 degrees Celsius. Remember to include the units of measure, as this is a problem in context. And finally, find the rate of increase 9 minutes after the oven is switched on. So we know that in part D we have theta is 198 minus 180 e to the minus kt. So d theta dt we differentiate, as we are looking for a rate of change, is minus 180 times minus k e to the minus kt. Notice that I do not put the value of k to be whatever I found. It will make the expression messy here and will increase my chances of making a silly mistake. Instead, I write everything in terms of k. So when I come to evaluate d theta dt when t is 9, this will be 180k e to the minus 9k. Once more, I plug everything on the calculator. I get 7.33 degrees Celsius per minute. Question 6, we start by being asked to find the derivative of f of x here. So I'll be using the product rule here, as we've got the product of x and cos of x over 3. So we differentiate the first one, we keep the second, cos of x over 3, plus keep the first and we differentiate the second, it's minus a third sine of x over 3. So this is cos of x over 3 minus x over 3 sine of x over 3. In B, we need to show that the equation f dash of x is 0 can be written in this form. So I will start by saying that if we want f dash of x to be 0, this simply means that cos of x over 3 must be equal to x over 3 sine of x over 3. The only way of getting tan into the game is for me to divide throughout by cos of x over 3, which takes me to 1 on the left hand side being equal to x over 3 tan of x over 3 on the right hand side. And now we'll try to isolate tan x, so I can say that 3 over x is tan of x over 3. So arctan of 3 over x is equal to x over 3, which leads to 3 arctan of 3 over x is equal to x, and therefore k is 3. In C, we need to use easy iteration formula. Starting with x1 is 2.5 to find x2 and x6 to 3 decimal places. So we are using the calculator here. We start with x1 being 2.5, plugging in this initial value into the given iteration formula. We get that x2 is 2.628, and if we continue doing that, we end up with x6 being 2.586. And then in part D, we need to use a suitable interval to prove that the solution is 2.581 to 3 decimal places. So I will take a tied interval around 2.581. I'll go 5 up, 2.5815, and 5 down, 2.5805. And I will look for a change of sign. Remember, we always substitute in whatever we need to be 0. In this case, we want the first derivative to be 0. So f dash of 2.5815 is equal to minus 3.46 times 10 to the minus 4. And f dash of 2.5805 is 3.47 times 10 to the minus 4. So there it is, we've got the change of sign. And therefore we can say change of sign in f dash of x continuous, hence root exists in this interval, which runs to 2.581 to 3 dps. In question 7, we need to prove the identity given here. So I will start from the left hand side. So the left hand side is sine of 2x over cos x plus cos of 2x over sine x. I will be expressing everything over the same common denominator of cos x sine x. So I'll be multiplying sine 2x by sine x, and then cos of 2x by cos x. Now the numerator resembles the addition formula for cos A minus B. So we can see that in our case, the 2x is the A and the x is the B, which means that in the numerator we will be having cos of 2x minus x. In the denominator it's the cos x sine x. Now the numerator is simply cos x, and this will simplify with the cos x in the denominator. I'm left with a sine x in the denominator. 1 over sine x is simply cosec x, which is the right hand side as required. In part B, we need to solve the given trigonometric equation given here. So we first spot that this part here, the sine 4 theta over cos 2 theta plus the cos 4 theta over sine 2 theta, is simply cosec of 2 theta because our x has been replaced with 2 theta. So the first thing I will do is write down that we have 7 plus cosec of 2 theta is equal to 3 cot square 2 theta. Now we have an identity that connects cosec squared and cot squared. So we know that cot squared is cosec squared minus 1. And these will lead to a quadratic in cosec. So 7 plus cosec 2 theta is 3 cosec squared 2 theta minus 3. I will collect everything on the right hand side. It's 3 cosec squared 2 theta minus cosec 2 theta minus 10. This factorizes into 3 cosec 2 theta plus 5 and cosec 2 theta minus 2, which means that cosec 2 theta is minus 5 over 3, or cosec 2 theta is 2. So sine of 2 theta is minus 3 over 5, or sine 2 theta is a half. We are in radian mode. We'll get the principal value, so the PV is shift sine of minus 3 over 5, which turns out to be minus 0.6435, and therefore 2 theta is the PV plus 2 pi k, or 2 theta is pi minus the PV plus 2 pi k. Dividing throughout by 2 gives me that theta is minus 0.3218 plus pi k, or theta is 1.8925 plus pi k. Similarly, on this side here, my principal value will be shift sine of a half, which is pi over 6. So 2 theta is pi over 6 plus 2 pi k, or 2 theta is pi minus pi over 6 plus 2 pi k. I'll divide throughout by 2 to get that theta is pi over 12 plus pi k, or theta is 5 pi over 12 plus pi k. And therefore, within the range of values of theta between minus pi over 2 and pi over 2, we get that theta could be minus 0.322, minus 1.25, pi over 12, and 5 pi over 12, a total of 4 solutions. In question 8, we are told that the percentage of the population of a small country having access to the internet is modeled by this equation here, and using the data for 2005 to 2010, we have plotted log P against T, and we find that the points lie approximately on a straight line with gradient 0.09 and intercept 0.68. We need to find the value of A and the value of B. So since we are told the gradient and the y-intercept of this straight line, we can say that log of P base 10 is equal to 0.09t plus 0.68. We know that the model is of the form P is AB to the T. It makes sense to take logs of both sides in order to compare. So log of P is log of AB to the T base 10. So log of P base 10 will be log of A base 10 plus log of B to the T base 10, which leads to log of P base 10 is log of A base 10 plus T log B base 10. I can now compare. Log A is the constant term, it's the y-intercept, it's the 0.68. Log B is the 0.09, it's the intercept, and therefore we have that log of B base 10 is 0.09 and log of A base 10 is 0.68. So B is 10 to the 0.09, which turns out to be 1.23, and A is 10 to the 0.68, which is 4.79. In B, we are asked to give a practical interpretation of the constant A. So we can say that we have already established that P is 4.79 times 1.23 to the power of T. We observe that when T is 0, P turns out to be 4.79, and actually that's the percentage of the population that had access to the internet at the start of 2005. And then in part C, we need to estimate the percentage of the population that had internet at the start of 2015. So at the start of 2015, that means that our variable T takes the value of 10. So I will substitute T is 10. So when T is 10, we have that capital P is 4.79 times 1.23 to the power of 10, which turns out to be 38, and therefore 38% of the population had access to the internet. Question 9, we've got to find this indefinite integral. So in the numerator, we've got 3x minus 2. In the denominator, we've got 3x squared minus 4x plus 5. We observe that the derivative of the denominator is 6x minus 4. So it would be great if I had this exactly in the numerator. So I could multiply the numerator by 2 to get 6x minus 4 over 3x squared minus 4x plus 5. And to counterbalance this, I multiply out by a half. So now that the numerator is the derivative of the denominator, this simply is a half ln of the denominator 3x squared minus 4x plus 5, and a plus c because it's an indefinite integral. In I, it's the integral of e to the 2x over e to the 2x minus 1 to the power of 3. I will start by writing that as the integral of e to the 2x times e to the 2x minus 1 to the negative 3 dx. The derivative of the bracket here is 2e to the 2x, so I will multiply e to the 2x by 2 to make it be the derivative of the bracket, and I will multiply by a half outside. So this will be a half times e to the 2x minus 1, and we increase the power by 1, we divide by the new power plus c, and this is equal to minus 1 over 4 brackets e to the 2x minus 1 squared plus c. In question 10, part A, we need to find the x dy in terms of y. So we start by writing down that x is 3 sec of 2y squared. So dx dy will be 3 times, and we get the power down, we deduct 1 from the power times the derivative of the bracket. The bracket is sec of 2y, so its derivative will be 2 sec 2y tan 2y. And this simplifies to 12 sec squared 2y tan 2y. And B, hence show that dy dx can be written in this form. So I will actually start by saying that x over 3 is sec squared 2y. We know that sec squared is 1 plus tan squared, so x over 3 is 1 plus tan squared 2y. So x over 3 minus 1 is tan squared 2y. So x minus 3 over 3 is tan squared 2y, which means that the square root of x minus 3 over 3 is the tan of 2y. So I now know that in the expression for dx dy, I will replace tan 2y with the root of x minus 3 over 3, and sec squared 2y will be replaced with x over 3. So dx dy is equal to 12 times x over 3 times x minus 3 over 3 square root. Now the 12 with the 3 simplify to give me a 4. And so I will be looking at dy dx, reciprocal of the above. So it's gonna be the root of 3 over 4x times root of x minus 3, which matches the form of the answer that was asked for in the question here. And C, we need to find the equation of the normal where y is pi over 12. So I will start by finding the value of x when y is pi over 12. So x is 3 sec squared of 2y, which turns out to be 4. I will evaluate dy dx at x is 4. So this will be the square root of 3 over 4 times 4 times the root of 4 minus 3, which turns out to be root 3 over 16. And therefore the gradient of the normal, I flip and I change the sign. It's minus 16 over root 3, which is minus 16 root 3 over 3. I'm using y minus y1 is mx minus x1, so y minus pi over 12 is minus 16 root 3 over 3 times x minus 4. I will expand to get y minus pi over 12 is minus 16 root 3 over 3 x plus 64 root 3 over 3. Which means that the final answer will be that y is minus 16 root 3 over 3 x plus 64 root 3 over 3 plus pi over 12.